going to start this lesson by just introducing free software that you can use to help you discover certain things about geometry and geometric figures. So I'm going to be using this. I used to use Geometry Sketchpad, but that's not free, and they came out with this GeoGebra program that's absolutely free. You just go to GeoGebra, so it's a combination of geometry and algebra, geogebra.org, and this page will come up, and then if you just hit download, you can run it in the Internet Explorer, whatever web browser you use by using this, or if you just hit one of these, it'll download it right to your computer, and you can use that. I'm going to be using it to start my lesson for Chapter 5. I'm going to show you a couple things you can do with it, and then I'll put some separate videos up to show you some more advanced techniques that'll be optional if you guys want to use it as a learning tool. It's very effective. It cuts out the need for you to do the constructions by hand, so if you're trying to quickly do a bunch of constructions to figure some stuff out, it's a great program. So we're going to start Chapter 5 just by talking about how we can find distances between two things. So it's pretty easy to find the distance between 2 points, but in this chapter we're going to also have to talk about distance from a point to a line. So if I want to know how far away is this point from this line, basically I'm asking, which line am I going to connect to this line and say, well, that's the distance. Okay, because there's an infinite number of lines that I could connect and then measure to find the distance here. But the one that we're actually going to be looking for is the shortest one. If you think about the shortest way to get from a point to a line, it's going to be the line that's perpendicular to the other line. Okay, so this line is a standard way of saying this is the distance from this point to this line. There's only one line that's going to do this, okay, according to our perpendicular postulate. So that way, if I say the distance from this point to this line, there's only one right answer if we define it as the line or the segment that's perpendicular to that line. So when I say how far away is that point from that line, you're going to have to measure the segment that's perpendicular to it. The other thing we're going to talk about is equidistant. So equidistance is equal distance from multiple objects. So let's say I wanted a point that was equidistant from this line and this ray. Okay, if this point's going to be equidistant from those two things, then the length of this perpendicular segment would have to be the same as the length of this other perpendicular segment. Okay, so if these were the same, this point would be equidistant from this ray and this line. Okay, because it's the same distance away from the two objects. To be equidistant from 2 points, okay, so let's say I've got 2 points on here. If I want a point that's equidistant from those 2 points, then that just means it's got to be the same distance away. So if this point's going to be equidistant, it's got to be the same distance from that point as it is to this point. So these would have to be congruent. That's how you're equidistant from 2 points. So equidistant from 2 lines is the perpendicular segments are congruent. Equidistant from 2 points, the segments connecting are congruent. So we're going to take this idea and start looking at some things that we've already done before. So we're going to look at a perpendicular bisector, which was one of the first constructions that we made, and we're going to try to get a theorem from it that we can use so that if I see a perpendicular bisector, I get more than just a right angle and a midpoint. Okay, I want more from it. So I'm going to construct a perpendicular bisector using my GeoGebra program here. So if you remember how to construct a perpendicular bisector, I need to make 2 circles, okay, one from this point and one from this point, to have the same radius and are more than halfway. So I'm going to make a circle with a center and a radius. Okay, I want it to be this center, and I want the radius to be 5. Okay, that's more than halfway. And I want a circle from the other point that has the same radius. Okay, so I get this. Now if I connect these points, okay, so there's one intersection, there's the other one. If I connect those, let's connect them with a line here. Okay, now I want to find out what's true about points that are on this line. What's true about points that are on my perpendicular bisector? Well, if you look at how I made this point, okay, this is one point that's on my perpendicular bisector. It's sitting on these two circles that I made, and these circles have the same radius. So point C is equidistant from A and B. So if I construct some segments here, okay, just going to make some segments here. Now if you see E is 5 and F is 5, this is segment E, this is segment F. They're the same distance. Okay, they're both 5, which is what I set my radius to be. Now, what I'm going to ask you is, if I make another point on this line, okay, is there going to be two circles I can make that have that same okay, that one and that one? Are these circles going to have the same radius also? Well, let's measure our radius by making another segment. That one's 2.95. Okay, they're both 2.95. That's going to be true for every point that I put on this perpendicular bisector. Okay, because this is my perpendicular bisector. And I could make any size circles. Okay, and I can change them around here. Okay, but no matter what I do to it, those points that are on there, okay, so now E is 3 from A and 3 from B. Every point on your perpendicular bisector is always going to be equidistant from the endpoints of the segment. And that's our first theorem that we have. So it's a perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. So here's a more simplified picture. I have a segment right here. We'll call it segment PQ. And this is the perpendicular bisector of PQ, because it's perpendicular and it's bisecting it. Any point that I put on here, okay, let's say this is point D. D is on the perpendicular bisector, so it meets the if part. Therefore, the then part is true. It's going to be equidistant from P and Q. So I would know that dP is going to be congruent to dQ by the perpendicular bisector theorem. Okay, I can make another point here. E. Okay. EP would be congruent to EQ. By the same reason. I could put one down here. Okay. FP is congruent to FQ. Same thing. Okay, any point I put on there. Okay, so if I have a point on there, I could make segments that connect them. Okay, and since those segments are the distance from the point on the perpendicular bisector to the endpoints, I would immediately know that they're congruent according to the perpendicular bisector theorem. Now, the converse of this is also going to be true. If a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. So here I've got this point here. It's the same distance from my endpoints, so let's name our endpoints CD. Okay. Point M here is the same distance from C as it is from D. So M is going to be on the perpendicular bisector. Now, what I need is one more point that's on the perpendicular bisector so I can actually draw in my perpendicular bisector. Because you can't draw a line with just one point. And I don't know where the midpoint is of my segment. So if you look down here, this point is also the same distance from D as it is from C. So N is also going to be on the perpendicular bisector of segment CD. Therefore, I can connect these with a line and know that this is the perpendicular bisector. So from the perpendicular bisector converse, I'm going to get that this is perpendicular. Okay, because M and N are both on the perpendicular bisector, so if I connect them, I get that it's perpendicular and it's bisecting my segment. Okay, we're going to look at the other construction that we started off learning, which was an angle bisector. So I'm going to make an angle. Okay, so I've got an angle here. Actually, I'm going to make it a different way. I don't want to measure anything. So I'm just going to make a couple rays. I need this. I need a ray. And another ray. Okay, if you remember how to construct an angle bisector, the first thing we did is we'd make a circle centered here. Okay, and that set up 2 points that we used, this one and this one, that we used to bisect the angle. Okay, and then I'd make 2 circles that were the same size. Okay, so I got these 2 same size circles. Okay, they're meeting right. Let's see if they're actually meeting it. Let's get rid of this point G. We'll do it this way. So that's where I want my center. We'll do 5 again for my radius. 5 again for my radius. Now where these meet, right here, I'm going to put a point. Okay, so I'm going to make sure it's highlighting both. This point is only on one circle. This one's on 2. Okay. If I connect that to my vertex, that's going to make an angle bisector. Now, this angle bisector is constructed in such a way that I've got distances from here to here that are the same as distances from here to here. Okay, so what we're going to do is we're going to draw another picture of this that makes it a little simpler and find out what has to be true. Okay, because I want to know what's true about every point that's on this line now. Okay, we're going to look at this point here where my circle I started with is meeting my angle bisector. Now if I change my circle, okay, the thing that's always going to be true about that point H is that it's always going to be the same distance from here as it is from here. So it's going to be equidistant from the 2 sides of the angle. Okay, no matter where I put it. So if I made a bigger circle, it's still going to be on the angle bisector, and the distance from H to this line is going to be the same as the distance from H to the other side of my angle. This, which I'll prove in class later, is the angle bisector theorem. And the proof of it requires some congruent triangles that we'll get into. Basically, if a point is on the angle bisector of an angle, then it's equidistant from the two sides. And remember, distance from two sides, so two lines, so if this is the point, that means the segment that's from here and perpendicular to here is going to be the same as the segment from here and perpendicular to the other side. So these are going to be congruent segments. Okay, and just a real quick proof of this comes from, if I set up my perpendicular segments here, I got right triangles, so I have this right triangle, and I have a leg and a hypotenuse, because the hypotenuse would be reflexive. Or actually, I'd have angle, angle, side, which makes these triangles congruent, which gives me these pieces congruent. I also have a converse of this theorem. So if a point is on the interior of an angle, so it's in between the two sides, and it's equidistant from the sides of the angle, then that means it's on the bisector of the angle. So if I knew that the perpendicular segment connecting this point to both sides, okay, if I knew that these were congruent, then I would know that this point's on the angle bisector, and I could then construct my angle bisector by connecting the vertex through that point. Okay, because I would have 2 points, because the vertex is always on your angle bisector. I would know that this is the angle bisector from the angle bisector converse, which would allow me to mark these angles congruent. Okay, and that covers the first section of chapter 5.